Hello, everyone. Let's get started on some organic chemistry here. So this is just going to be an introduction to organic chemistry. This whole sort of series, this whole week will be about really building on your knowledge of structures, molecular structures that you started in general chemistry, reminding you of all those key features of, electron shapes and how atoms are connected and all that good stuff, all right? First thing we need to do, though, is just answer what is organic chemistry, right? What can we expect about this course? What is organic chemistry that's different from other chemistries, inorganic chemistry, for example? So you'll often hear it said that, kidding, you're killing me, knocking at this cord. All right, so you'll often hear it said that organic chemistry is the study of carbon-containing molecules, okay? And so it is, in the strictest of sense, we consider a molecule to be organic if it's a hydrocarbon, okay? Hydro meaning that it contains hydrogens, carbon meaning that it contains carbons, okay? So if you're a hydrocarbon, you're an organic. Purpose of this course is to build to this point where we can understand chemical reactions that occur between organic molecules. One of the big questions is going to be this: why do reactions occur? All right. We're going to need 2 semesters to go through the major functional groups in organic chemistry and to answer how they react. One of the things that you're going to see over and over and over again, though, is that electron-rich species will react with electron-poor species. That's the basis of a chemical reaction in organic chemistry. So one of the things that you should do during these series of lectures when we're talking about structure is start to think of that idea of electron density. Where do electrons sort of lie on a molecule? Are there portions that are more electron rich and portions that are more electron poor? All right, because they're going to be some key players here as we go forward. Again, the elements involved, the big ones are, again, hydrogen and carbon. And then we'll, generally speaking, be paying attention to some of these other guys as well. To be honest, not really silicon. Phosphorus and sulfur may play a role. Also, I would include all of the halogens, so bromine as well. But these are the players that we're going to see over and over again. That's kind of nice, because that means that we are focusing mainly on this first row of the periodic table, where things are actually a little bit more simple, electronically speaking, in terms of the electrons, than it is down here, where there are many more electrons and there's many more sort of weird stuff that happens. So we're going to focus ourselves up at that second row there. Okay, so just to compare to inorganic chemistry, which if you're a chemistry major is a course that you will eventually be taking. Again, our compounds are all made of hydrocarbons in organic chemistry. Inorganic chemistry, those are talking about salts or metal compounds. So if you have, so a salt is just an ionic compound where the cation is a metal, right? Those inorganic compounds are held together by ionic bonds, whereas our organic compounds are held together by covalent bonds. Covalent bonds are a lot more complicated. Making and breaking of covalent bonds is a lot more complicated. So that's why this is this whole sort of study of organic chemistry focused just on organic molecules and their reactions. This concept of functional group is going to be important. That's essentially the portion of a molecule that does the reacting. And next chapter, we'll introduce some functional groups. But those groups are responsible for the reactions, whereas in inorganic chemistry, it's more like redox reactions, exchanging of electrons. Organic compounds are handled differently. The laboratory portion exists because you have to handle organic compounds differently than metals and salts. They melt and boil more easily. One of the more striking things is that organic compounds are much more likely to be liquids. Only at very high temperatures are metals and salts going to be in the liquid phase, and never in the gas phase, really, unless you're talking about in space or whatever. So this is one of the unique things about organic compounds. And the other sort of thing that makes it very interesting is it relates to biology, in that organic chemistry is the chemistry that's happening on our Earth's surface. That's where most of that carbon is that's sort of in use reactivity-wise. Chemistry at the Earth's core or out in space, that's more of inorganic chemistry, okay? So one of the key takeaways of this lecture is going to be introducing this concept or this definition for a constitutional isomer. Okay, so now we have a molecular compound here represented by its molecular formula. That of course tells you how many carbons there are, hydrogens are, and oxygens in this particular molecule. But we are talking about covalent molecules, right? So the linkages of these atoms is very important. And it turns out that you can do so two different ways. All right, these are the same number of carbons, same number of hydrogens, same number of oxygens, just linked together differently. The key portion being here we have this carbon-oxygen-carbon bond, whereas here this is an alcohol group, carbon-oxygen-hydrogen. All right. Or I guess carbon-oxygen and then oxygen-hydrogen. So basically this chemical formula, this molecular formula rather, it's not quite enough information to specify a molecule uniquely, okay? It's certainly a lot of information. These two would be considered to be constitutional isomers. They have the same molecular formula, but different connectivity of atoms, all right? So that is a definition of a constitutional isomer. This is an example of a pair of constitutional isomers. One thing I do want to point out is by connectivity of atoms, the spatial placement in the drawing is not important at all. So for example, if I had something like this, this is the exact mirror image of this compound down here. This is still ethanol. These are identical, right? So these guys right here are identical. They are both ethanol. It's just a different way of drawing the exact same molecule, all right? So that's what you're sort of going to need to be able to distinguish here is, are these two pair of molecules constitutional isomers? Are they identical, or are they just completely different altogether? One of the things that's nice about organic chemistry, that's nice about paying attention just to that row 2, is that the rules for bonding or the bonding patterns are a lot more simple than they are for the bigger molecules. In particular, this box right here sums it up very nicely. Basically, you can tell whether or not a structure is a legit structure fairly easily, because carbon is going to always have 4 bonds. Nitrogen is going to always have 3 bonds. Oxygen is going to always have 2 bonds. And then either the halogens or hydrogen, both of those only have 1 bond. What's missing from these drawings are the lone pair of electrons. So if I just put those in for completeness here, there's none on hydrogen, and then the halogens have a full 6, okay? But yeah, so that's how you can tell. We will see cases where structures have 4 bonds. For nitrogen, for example, where nitrogen has 4 bonds, but then it also has a formal charge. It has a charge associated with it then. So the only way to get like a neutral molecule, which are typically the most stable, is to have this sort of bonding pattern right here. All right, so that's an easy way to check whether or not a structure is legit, okay? And we'll work on building these, what are called Lewis structures, later in this lecture. We actually got to do a little bit of groundwork first, talking about the shapes of atomic orbitals. So yeah, so before we can even get there, we'll have to go to bonding. All right, so yeah, do your assignment and then click over to the next set of videos. It's good to practice this stuff directly after the lecture. That's the intention, because that'll sort of harden that bond and that understanding in your mind.